This video will teach you how to measure steady-state spectra using a xenon lamp and an Edinburgh FLS980 spectrometer, and also show you how to measure nanosecond lifetimes excited by a pulsed diode laser. This tutorial is intended for first-time users that are being trained on the instrument at the foundry. The idea is that you would follow along with the video while you're sitting at the instrument performing your own measurements. While the operations here are specific to the foundry, these instructions may be useful for users of other Edinburgh FLS spectrometers. The Edinburgh FLS980 spectrometer is an instrument for measuring steady-state and time-dependent luminescence spectra. It has double excitation and emission monochromators and a variety of excitation and detection schemes. It has both visible and near-infrared detectors that can span the range of 200 to 1700 nanometers. It has a variety of detection modes, including steady-state luminescence, time-correlated single-photon counting for nanosecond lifetimes, and also multi-channel scaling for microsecond and millisecond lifetimes. Luminescence can be excited using steady-state and flash xenon lamps, where the wavelength is selected by the excitation monochromators. Or you can use picosecond pulsed laser diodes to perform time-correlated single-photon counting. You can also excite samples with high-powered near-infrared lasers available at 800 nanometers and 980 nanometers. These infrared lasers can operate in both continuous wave mode and also with nanosecond pulses, which we use for microsecond and millisecond lifetimes. In this video, we'll cover turning the system on, running a steady-state emission experiment using the xenon lamp as the excitation source, measuring nanosecond lifetimes using a picosecond diode laser as the excitation source. This will be done in time-correlated single-photon counting mode, shutting down the instrument, and also going over a few troubleshooting tips. Chapter 1. Starting up the spectrometer. The first thing you want to do when you first get to the instrument is to turn on the pH1 switch, which turns on the power for the spectrometer. Next, you'll turn on the CO1 switch, which turns on the power for the PMT. It will take about 30 minutes for the PMT temperature to stabilize below -21 degrees Celsius, but the longer you can wait, the less noise you'll have in your detector. So you should always plan to wait at least 30 minutes before you start doing your experiments. Next, turn on the xenon lamp. The xenon lamp is shown here on the schematic on the left. There's a silver button on the top of the lamp module. When the LED screen says ready to start, press the silver button. You should always wait 15 to 20 minutes for the lamp to stabilize if you're doing quantitative measurements. Since you have to wait for the detector to cool down anyway, this should not be a problem. Next, you want to make sure that there's no prism blocking the beam path for your excitation light source. People who use the near-infrared lasers will insert this prism to steer their laser beams into the sample chamber. If this is true, you want to flip the prism 90 degrees clockwise as shown in this left-hand figure. Or you can look at this photograph of the sample chamber. The prism is located on a flip mount, and so you can flip this flip mount to move the prism out of the way by turning the rod from the vertical position to a horizontal position. If you do this right, the excitation beam will no longer be blocked by the prism, and you can excite your sample in a cuvette or a solid sample holder. Next, you'll open the F980 software, whose icon sits on the desktop of the Windows computer that's located on top of the Edinburgh instrument. When you double-click this icon, it'll open up this F980 splash screen, and you'll see various messages telling you which parts of the spectrometer are initializing. Chapter 2. Acquiring a steady-state spectrum using excitation from the xenon lamp. So now we're ready to measure spectra of our samples. So we need to load our samples into the sample holder. First, we're going to make sure the laser is off. Then we'll open the sample chamber cover shown here. If you're using liquid samples, install the cuvette holder and mount the beam block onto the filter holder slot of the cuvette holder. If you're using solid samples, you need to install this angled solid sample holder. Next, you'll attach the translation rod into this moving stage into the front panel of the sample chamber. So the knob is used to rotate the translation rod and then move the solid sample holder back and forth so that it can translate across the beam. This is a little tricky, so you can lift up this panel up and away so that you can reach into the sample chamber a little easier. Look at the video for how I do this. You can replace the panel and close the sample chamber. The solid sample holder has a second piece that's a clip that can clip onto a glass slide or a cover slip. You can see me clipping in this cover slip that has my dried sample into the clip assembly, and then I can slide this clip into the angled solid sample holder base. So once I can do that, I'll close up the sample chamber. So now we're ready to set the software settings. When you opened up the F980 software, it should have automatically opened up the signal rate window. But if you don't see it, you can click this icon in the leftmost side of the toolbar. It looks like 3 different bars. The signal rate window is really important because it gives you a live measurement of the intensity of light measured by the detector. In order for this to be a useful measurement, we need to set up the spectrometer correctly. First, select the source light path. Here we're going to set this source as XE1 for the steady state xenon lamp. If we're using the microsecond flash lamp, then we'll select micro F2/MCS. Later on in this video, we'll choose the TCSPC option for measuring lifetimes using the picosecond pulse laser diodes. Next, we'll set the grading. So here you'll choose the grading with the label that corresponds to the wavelength that's closest to your peak emission wavelength. Next, we'll set the excitation wavelength. This is important for lamps because this controls the excitation monochromator. If you're using the infrared or the picosecond lasers, then this doesn't do anything. We can set the excitation bandwidth or the slit width. This controls how much light gets to your sample. The smaller the slit width, the less light gets to your sample, but the monochromator will have finer resolution. Most of the time, if your absorption spectrum is very broad, then it doesn't really matter how much resolution you have in your excitation monochromator. But if your bandwidth is too broad, then you could end up having light leak into the regions that you're measuring for your spectrum. Next, you'll set the emission wavelength to the wavelength of the peak of interest. You'll also set the emission bandwidth to 0.1 nanometers. This sets the slits, and right now we're going to close the slits down as small as possible to avoid saturating the detector. So once you've set your excitation and emission wavelengths, you should be able to see the emission 1 signal fluctuate over time. Ideally, this signal should be anywhere between 10 to the 5th to 10 to the 6th counts per second. Anything higher than that is bad because you're saturating your detector, which is the PMT in this case. So normally, since your slit widths are very small, you want to open up the excitation slits to something around 1 to 2 nanometers, and you also want to increase the emission slit to 0.5 to 1 nanometers. You can continue increasing the bandwidth of these slits, but keep in mind that increasing the excitation bandwidth too much will start causing the lamp to bleed into your emission spectrum, and increasing the emission slits too high will start to broaden the features of your emission spectrum because you're changing the resolution of your monochromator. There's a couple other ways you can optimize the emission 1 signal. If your signal is too high, you can install a neutral density filter in the excitation or emission beam paths. You can also adjust the position of the solid sample holder by turning the translation knob. This will change both where the laser is focusing on your sample and how it reflects into the emission monochromator. So finally, you're going to exit the signal rate window. You can click Apply and then close the window. To actually set up an emission scan, you can click on this lambda button, and then you can set the start and ending wavelengths for your spectrum, along with the step size in nanometers. Next, you'll set the dwell time or the integration time at each wavelength step. You should set this somewhere between 0.1 and 0.3 seconds. Anything longer than that doesn't really increase your signal to noise. To increase the signal to noise ratio, it's actually better to increase the number of scans. Click on the Correction tab to set the spectral correction parameters. Here it's recommended that you check the Subtract Background box. This baselines the signal to a dark reference. Since we're using the xenon lamp, you want to check this Correct By box. This will correct for variations in the intensity of your lamp at different wavelengths. It is recommended to check the emission 1 file in the emission correction box. This corrects for the different sensitivities of the PMT detector to different wavelengths. It's not a big deal if you don't check this box because you can always correct your spectrum later. It is important to choose the Subtract Background box if you are correcting your spectra. This is because you don't want to apply a correction factor to a baseline that's not your actual signal. So now we're ready to acquire our spectrum, so you want to click the Apply button and then start acquiring the spectrum. After you click Apply, you'll see a window pop up that has your spectrum. This yellow line is your spectrum filling up the screen as the monochromator scans through the different wavelengths. If you chose multiple scans, this will cycle through the wavelengths multiple times, and it will add on the new counts onto the old counts. Note that the values here are negative because the dark signal has been subtracted from your main signal. When you're done, you can go to the File menu and then select Save. Be careful not to overwrite your files. It's really easy on this version of Windows because when you click on another file, instead of giving you the option to rename your file, it will automatically try to save your file as the same name. It will give you a warning, so it's important that you say no when it asks you whether you want to overwrite that file. You can also export your data by going to File, Export to ASCII, and this will produce a text file. Chapter 3. Measuring lifetimes in time-correlated single-photon counting mode using the picosecond pulsed diode lasers. Before you use the picosecond lasers, you want to take a beam block that normally protects the picosecond laser and move it in front of the near-infrared laser instead. So on the right, you can see a picture of this beam block. It's normally mounted on a Thorlabs freestanding mount. And this is how it would be both in front of the picosecond laser and also in front of the near-infrared laser. Next, you want to make sure that the desired laser is installed. So we have two different lasers, the 375 nanometer laser and the 485 nanometer laser. Only trained super users may reconfigure and align these lasers because they must follow proper laser safety protocols. So if you need a different laser, please ask a super user to install the correct laser for you. Next, you'll set the pulse period or the repetition rate of the laser. You can do that by adjusting this red dial at the bottom of the picture on the right. Don't set the pulse rate shorter than 200 nanoseconds, which is equivalent to 5 megahertz, since 5 megahertz is the maximum read rate of the electronics that count the pulses. Before you turn on the laser, it's recommended that you turn the optical power all the way to its minimum value. You can do this by turning this dial, which is actually a neutral density filter wheel. Next, you'll turn on the laser diode power supply by turning the key. Next, you'll actually turn on the laser emission by pressing this red button. Only press the on-off button if the sample chamber lid is closed, since this is a Class 3B laser. In the future, if you want to change samples or open up the sample chamber, turn off the laser using the red button or by turning the optical power all the way down to its lowest setting. Next, disconnect the trigger BNC cable from the microsecond flash lamp. The diode lasers may not work if this cable is connected. Next, I'll open up the signal rate window, and then I'll set the emission bandwidth to 0.1 nanometers because I'm going to start changing the system and I want to protect the detector. Next, we'll set the source light path. We'll change it to TCSPC, which stands for time-correlated single-photon counting mode. We'll click Apply, and then you should now see both counts for the TCSPC laser as well as the emission 1 counts. So the emission 1 counts should always be less than 3% of the laser counts in TCSPC mode. This is so that you make it extremely unlikely that 2 photons would be counted in the same time bin. Typically, your count should be somewhere between 10 and 100,000 counts per second. If you're not seeing enough counts, you can also adjust the emission slits. Typically, you would open up these slits, which isn't really important because we're not trying to collect spectra. Other ways you can increase the count rate for lifetime measurements are turning the optical power knob up to increase your signal, or shortening the pulse period so that you achieve a higher number of pulses in a given amount of time. You can also adjust the solid sample holder if you're using it. You can turn the translation knob so that you can optimize the focal point of your laser onto your solid sample holder. Make sure to orient the solid sample holder so that it's facing the picosecond laser instead of the lamp as it appears in this case on the left. So once you've optimized the emission 1 signal, you can click Apply and then Close. It's usually a good idea to acquire a steady-state spectrum with your pulsed excitation before you run any lifetime measurement. This is because this will show you if there's enough signal to really get a good lifetime curve. Also, you want to make sure that there's not other peaks that are bleeding into your main emission peak. So when you run this emission scan, remember to uncheck the Correct By box in the excitation correction subpanel. This is because the correction file is built for the lamp rather than the lasers, which only emit at one wavelength anyway. Once you verify that your emission spectrum is correct, then you can click on this tau button and select Manual for a manual lifetime measurement. 2 windows will open up, the manual measurement window and then the TCC window. Let's take a look at the TCC window at the bottom. Here you can see that it shows you your pulse rate, which here it's 5 megahertz, and it also shows you the time range, which is currently set at 200 nanoseconds. So you want to make sure that this is longer than 2 times the expected lifetime, or ideally about the time that it takes your intensity to decrease about 3 orders of magnitude. You do want to make sure that this is less than 1 pulse period. So if your pulse period is 200 nanoseconds, then this time range can't be longer than 200 nanoseconds, or else you'll get more than 1 pulse per measurement period. Next, you'll set the number of channels. This is set at 4096 by default, but you can set it also to 512 bins. This will allow you to collect more data per bin. Next, you can set the stop condition. Right now, you can see it's set to stop when your intensity gets to a specified number of counts. I like to set it as the collection time, so for 10 minutes. Ideally, what you would do is you would first run a trial run at a short collection time and see if your data gives you approximately the right data. And then once you want to get a nicer set of data, then you can set for a longer collection time. So once you're happy with all your settings, you can click Apply. And then you can go to the manual measurement window and you can click New to start a run. So we can see a black window opens up, and then you'll see all the time points accumulate counts over time. Hopefully you should see a decay curve that looks like this. Here you can see the laser pulse is turning on and the counts are increasing. And then after the laser pulse turns off, then you can see the counts decrease or decay. After the acquisition of the lifetime data is done, then you can analyze your data by going to the Analysis menu and then selecting Exponential Tail Fit. This should open up the Exponential Tail Fit window. First, you can set the time range for which you're fitting. Usually the automatic or default values are pretty good. It will automatically select the highest point as the start of your fitting range. Next, you're going to set guess values for the lifetimes. Usually I would select 2 to 3 so that I'm doing a double or a triple exponential fit. So then I can click apply to do the fit, and it's usually very fast. So a second window will open up and it'll show your curve cut off to the fitting range, and it'll also show a blue curve that shows the fit. Below these curves will be the residuals. You want to just make sure that there aren't very large residuals or ones that are not completely random. So in the same exponential tail fit window that you use for your guesses, you'll see now that those values have changed, and these are the fit parameters for your curve fit. So these B1 and B2 values are the amplitudes of these two lifetime components. So you can see here that the tau1 is dominating. So again, you can see how these B1 components are related to the overall curve by looking at the equation. When you're happy with your lifetime fit, you can copy these fit parameters as text and then paste them into a text file. You can close the curve fit box, and then I would recommend saving the decay curve with the curve fit as a separate file. If you have short lifetimes on the order of 10 nanoseconds or less, you may want to use the reconvolution fitting option instead of the tail fit. This allows you to deconvolute the response of the instrument to your laser pulse from the response to your sample emission. This requires that you take a lifetime curve of your lamp response. Usually you would do this by placing a colloidal suspension of Ludox or silica nanoparticles, or realistically any other thing that scatters light. So that's measuring the lifetimes. You can see it's very simple in this software. Once we're done, we can shut down the instrument. To shut down the instrument, we would first turn off the xenon lamp by pressing the same silver button that we used to turn it on. Next, we would turn off the pulsed diode laser. First, turn the optical power down to its lowest setting by turning the wheel. Next, you would stop the laser emission by pressing the red on-off button. And then you would turn the key to turn off the power supply. Next, remove your samples from the sample holders and make sure to put them away. Don't leave them around the spectrometer. In general, when you're done with the instrument, you want to return the Edinburgh back to its original configuration because those are the default settings. In this case, since we had moved the beam block in front of the near-infrared lasers, we now want to remove that beam block and place it again back in front of the picosecond diode lasers. Remember to remove any excitation or emission filters from the beam path. This is really important, again, in case the next person is trying to view a wavelength range that your filter is blocking out. Finally, power off the instrument. You'll first make sure to wait 3 minutes for the lamp fan to turn off. Next, turn off box CO1, and then the pH1 box. Verify again that all of your light sources are off, including the lasers and the lamps. You're going to save all your data and exit the F980 application. Chapter 5, Troubleshooting. The Edinburgh spectrometer is pretty easy to use, but here's a few tips that will help you avoid common problems and increase the quality of your data. It's usually a good idea to measure a steady-state spectrum using the xenon lamp first before you move to the pulsed laser. If your sample is dim, you may be able to see the emission spectrum more clearly using the xenon lamp. Next, remember to acquire a steady-state emission spectrum using the pulsed laser just to make sure that the triggering is functioning correctly. Remember, when you're using the picosecond laser diode, turn the sample holder around to face the picosecond laser because they're in two different orientations. If you're not seeing any signal, check to make sure that the prism for the near-infrared laser is flipped out of the beam path. Another problem is that the pulse spectra do not show any signal, even though the continuous wave spectra do. So here you want to make sure that the BNC trigger cable connections are correct. Remember, you want to disconnect the trigger BNC cable from the microsecond flash lamp. If you observe a sharp decrease in the signal around 680 nanometers, or you see a bunch of sharp peaks in your visible range, then it's possible that your excitation source is bleeding into your emission spectrum. This could be due to scattering from your sample or just having a really dirty light source. So one solution is that you can install an emission filter that blocks out your excitation source, or you can install an excitation filter that can clean up your excitation source. There are colored glass filters in a drawer in a cabinet located underneath the Edinburgh spectrometer. You can mount these colored glass filters in emission filter slots or in the excitation filter slot. Please remember to remove these filters when you're done. So there are many other tricks to using the software and the hardware. We can't cover them all in this video. So if you have any other questions, ask a super user of this instrument. So in this video, we showed you how to turn the system on, measure a steady state emission spectrum with a xenon lamp, measure nanosecond lifetimes using TCSPC, shutting down the instrument, and also troubleshooting. There are many other features of the Edinburgh spectrometer that we don't have time to cover in one video. Check back on this same channel for videos that cover measuring spectra and microsecond lifetimes excited by infrared lasers or the xenon flash lamp, spectroscopy and lifetimes using the near-infrared detector, quantum yields, and also performing high-throughput microplate reading.